Hello, and welcome back to the course on classical electromagnetism. So this is now the last lesson for chapter 5. So let us first review some concepts before we proceed with this lesson. So in electrostatics, we discuss about linear dielectrics, wherein we discuss about the relationship, the linear relationship between the polarization and the electric field. So in the same manner, in this lesson, we will also present the linear relationship between the magnetization and the uh, auxiliary field and the magnetic field. So we introduced the quantity called electric susceptibility. So it's basically just how polarizable is your, how susceptible or how polarizable your material is. And epsilon is the general permittivity. It's 1 plus the susceptibility times the permittivity of free space. And we define the dielectric constant as the ratio between the general permittivity and the permittivity of free space. So in the previous lesson, I also forgot what's the difference between free and bound currents. So free currents, in the same manner as you have free charges, they are basically found on conductors. So basically, charges that are moving in conductors are free currents. And if you have material that is magnetized, and that's usually not a conductor, so it's an insulator, then you will be having bound charges if you are exposing it to an electric field, if you polarize it. But if you magnetize it, you will have bound currents, surface bound currents and volume bound currents. So for this lesson, we will be talking about the electric version of, or magnetic version of susceptibility and permeability. So similar with electrostatics, we'll only consider linear media. The media wherein the magnetization is linearly proportional to the auxiliary field. So this quantity here, C sub m, is what we call the magnetic susceptibility. So it's just the magnetic equivalent of electric susceptibility. It's positive for paramagnets, and ferromagnets, it's negative for diamagnets. So from our equation for magnetic field in terms of the auxiliary field and the magnetization, we can now write it directly as this. So B is now equal to mu, which is the general permeability times the auxiliary field. So if you will recall in electrostatics, the electric displacement is basically just epsilon times the electric field. So these are now the magnetic susceptibility and magnetic permeability. So permeability is basically just how permeable is your material to magnetic fields. So how is it? How does it respond to an external magnetic field? So that one. So mu naught again is the permeability of free space. So when mu is equal to mu naught, that means when the susceptibility is equal to 0, then it's a vacuum. There's no, so that case is basically a vacuum. That material is basically a vacuum. There's nothing, there's no material there, no matter to magnetize. So let's have an example. So find the magnetic field of a long solenoid filled with an insulating material with susceptibility C sub m, and what are the bound current densities. So in this example, we now have a conductor, which is our solenoid, and we have an insulator. So in our conductor, there will be free currents I. It's actually in this direction. The magnetic field is inside in this direction, so this is the direction of our free current. And there will also be bound currents in our insulator. So we are asked to find first the magnetic field inside. So if you will recall, the magnetic field inside a solenoid is equal to mu naught Ni over L. Say in this direction, if this is the z hat axis or the z axis, then the direction is z hat. Okay. So we will use Ampere's law for magnetized objects. So you have H dot dl is equal to free current enclosed. In this case, the free current enclosed. So our Amperean loop is actually like this now. Again, only this side will matter. This side of the loop, this side of the loop, and that side of the loop will not contribute to the integral. So the total current enclosed will be the number of wires enclosed. This is a solenoid, number of turns times the current I. So that is the total free current I, N times I. So again, this will just reduce to H and this just and dl, where dl is just that one, L and I. So therefore, the auxiliary field is just Ni over L Z hat. So again, the auxiliary field is in the same direction as our magnetic field. So this is now the auxiliary field. So to find the magnetic field, take note, this is the magnetic field without the insulating material, but the magnetic field now with an insulating material, so I'm just going to call this B naught, so you will not be confused. It will be mu times H. So mu is just mu naught times 1 plus the given susceptibility, and H is Ni over L. Z. So this is now our the magnetic field inside. So it's a combination of the magnetic field of a solenoid plus the magnetization in the insulating material. Okay, so the next question is, what are the bound current densities? So since this insulator is exposed to the magnetic field of a solenoid, it will become magnetized. So its volume current density will just be the curl of the magnetization. So in this case, the magnetization is actually the susceptibility times the auxiliary field in this case. So you will have the susceptibility, and the auxiliary field is Ni over L, Ni over L Z hat. So it's in the same direction as the magnetic field. So this is our magnetization. So we take the curl of that, but you will notice that all of these are constant. So therefore, there will be no volume currents, volume bound currents in our insulating material. And solving for the surface bound currents, we will have M cross N hat. So you will have the susceptibility Ni over L Z hat cross N hat. Now, our N hat in this case is the S axis. So the normal to this insulator material is this one. That's the S hat. That's our N hat, the axis. So Z cross S will give you P. So KB will be the susceptibility Ni over L P hat. So you will notice that the surface bound currents are in the same direction as our free currents. So the free currents in this direction, phi hat direction, and the surface bound currents at the surface of the insulator is also in this direction, in the phi hat direction. Okay. So these are the summary of our results. So the free current and the bound currents are moving in the same direction in this case. The free current in the solenoid and the bound currents in the insulator are moving along the phi axis. and there are no volume bound currents in this case. Okay. So in this example, you have a coaxial cable. So this is a very realistic example. You have a coaxial cable. So this is a conductor. So it's basically a conducting rod, and you have a conducting shell. And in between the conducting rod, the conducting shell is an insulator region. So in the conducting rod, the current is moving in that direction. In the conducting shell, the current is moving in the opposite direction. It's positive and negative. So just like what you find in your audio-video cables, RCA cables, and so on. Okay, so these two currents here are free currents. And inside, and in this region here, in the insulator region, where the susceptibility is this one, given by this one. So in this region, there will be bound currents. It's either volume or surface bound currents, or both. Okay, so you are asked to find the magnetic field in the insulator region first, and find the surface bound currents on the surfaces of the insulating region. So that one. So let's first solve for the magnetic field in the insulator region. So we use Ampere's law again for magnetized objects. So H dot dl is equal to free current enclosed. So since in this case our current are moving along the axis of the cylinder, then our Amperian loop will be circle. This circle. This is our Amperian loop. See with radius S. Okay. So the free current enclosed by this loop is obviously that one, I. The free current enclosed is I. So this is just reduces to H times the length of our loop, which is 2 pi S. So our auxiliary field is just I over 2 pi S. And the direction of the auxiliary field, if this is the direction of the current, the direction of the auxiliary field is curling around the current, so it's actually in the phi hat direction. So the direction of the auxiliary field is actually in the same direction as this is our H, and this is also the direction of our DL. So that H dot DL is just H DL. So they're both in the phi hat direction. Okay. So to solve for the magnetic field, it's just mu times H. So mu is just mu naught 1 plus the susceptibility times H, which is I over 2 pi S PM. So this is the magnetic field in the insulator region. Take note that if there is no insulating region, if this is 0, then this just reduced to the magnetic field of a current carrying wire, mu naught I over 2 pi S. Okay, so how about the bound currents? The bound currents. Okay, so we can now solve for the magnetization. It's just susceptibility times the auxiliary field. So you will get susceptibility times I over 2 pi S phi hat. So it's still in the phi hat direction. So to solve for J, the volume bound current density, we take the curl of this for the magnetization. So only the Z component of the curl will survive. So you have S, and then the phi component Z hat. But you will notice that if you multiply this is the phi component, because this is the phi hat direction. If you multiply that with S, then there will be no more S, and it's just a constant. So you take the derivative of S with this to a constant, this will give you 0. So in this case, there are actually no volume bound currents. Now for the surface bound currents, so this is M cross N hat. So you have the susceptibility I over 2 pi S phi hat cross N hat. Okay, if you look at this insulator region here, the N hat it has actually two surfaces. The surface at S is equal to A, this surface here, and the surface at S is equal to B, this surface here. So the n hat in this surface is actually in that direction. That's the n hat. It's actually negative S hat. And the n hat in this direction is in this direction. That's n hat. And this is positive S hat. So with respect to the two surfaces, so at S is equal to A, where n hat is equal to negative S hat. So if this is equal to negative S hat, then P cross S is actually negative Z, and then you have a negative sign, so you have positive Z. So you will have XMI over, CM over S. This is Z hat, positive Z hat. For S is equal to B, the second surface, the outer surface, where n hat is equal to positive S hat in that case, the direction of the surface current density is negative Z hat. That one. In the inner surface, the surface bound current density, KB, is in this direction. Sorry, S here is equal to A, and S here is equal to B. That one. So this is the magnitude of the surface current density at S is equal to A at this inner surface. So the current is actually along the positive Z axis, so in that direction. So in the same direction as the free current. And in the outer surface, the direction of the surface bound current density is negative Z hat. So it's in the same direction as the free current on the cylindrical shell. So in this direction. So both of the currents in the two surfaces are in the same direction as the corresponding free currents. Okay. Okay. So that is the end of this lesson and basically the end of this chapter. So for the next chapter, we will now be mixing electricity and magnetism. So we will now go into the field of electrodynamics. So I will see you again in the next chapter.